Welcome to the start of quarter 3 in physics. Before we get started with our new information, which will be waves, and just a couple of updates as we move into quarter 3. Taking some feedback, I have decided to move the due dates from Friday night to Sunday night. With all the different activities starting, I know that Fridays can be pretty jam-packed, and Saturday afternoon there's games and activities as well. Okay, so I am going to give you through the weekend to get everything in, but I really need it in by Sunday night. That means I will be waking up early Monday morning to get those graded before I see you on Zoom either Monday or Tuesday. Okay, so please make sure you get those assignments in on time by Sunday night. But once again, if you get everything in early, you don't have to attend the Thursday or Friday Zoom. Okay, so we will run it the same way as it was before. Thursday and Friday Zooms are required unless all your work is turned in early before the class period that I would normally see you. Okay, so if you have it done Thursday morning for first hour, then you don't have to come to the Thursday first hour Zoom. Thursday, Friday. And then as we move into quarter 3, I've kind of got a schedule set. There is a weekly plan that I kind of follow. First thing we do on Zoom is we do some type of a review, either questions or maybe a problem. Okay, there will be 1 to 2 assignments per week, depending on, I'm trying to get 1 problem set and 1 lab for you guys to work through. And then at the end, there'll be either a weekly check or a little quiz for you guys to do to check for understanding. Okay, so kind of keeping that in mind, I'm going to kind of try and keep that schedule the same as we worked through quarter 2, it'll be the same level of assignments. All right, here we go. So we are going to look at waves. Okay, a wave is a transfer of energy from one point to another with no transfer of mass. Okay, there's tons of different types of waves. Think of a light wave. From the sun, the light transfers to us or the plant, but it doesn't bring mass with it. So it's a transfer of energy. It brings us heat, it brings us light with no transfer of mass. If you watch a water wave, you're by the ocean, the wave comes up on the beach, it brings with it energy. You can tell because if you have footprints, it washes it away. But then the water goes back in. It doesn't stay on the beach. It moves back to the ocean. So it's a transfer of energy from one point to another with no transfer of mass. We are working with things that have a medium. That is the material through which a wave travels. Okay. Water, a wave travels through water. Air, sound waves travel through air to get to you. They can travel through metal. They can travel through all sorts of things. Okay, our 2 types of waves are going to be mechanical and non-mechanical. A mechanical wave is a wave that needs a medium to move their energy from one place to another. This is going to be most of the ones that we deal with right away. Okay, so a water wave, it has to have water, otherwise it's not going to work. A slinky, if I move a slinky up and down, it needs that slinky, that's the medium. A sound wave, it has to have air molecules in order to transfer the sound, otherwise it does not work. There are 2 types of mechanical waves that we're going to look at. So these are going to be the 2 types of waves that we spend our time on. A transverse wave is a wave whose particles vibrate perpendicular to the direction of the motion of the wave. And perpendicular means at a 90-degree angle, so the molecules are going to move up and down, but the wave is going to move side to side. Okay, so perpendicular, the molecules are going to move up and down, the wave is going to move side to side. I'll show you an example of this in a second. Thinking of an example, a stadium wave. If you've ever been at a baseball game and you have to stand up to do the wave, it's not really a wave, but pretend like it is. Each individual person stands up and goes up and down, but the wave transfers through the stadium on the side-to-side motion. Okay, so up and down, but side to side. Same thing with a rope moving up and down, or a slinky. I didn't have a rope. If I take my hand on one side and move it up and down, my hand is moving up and down, so it's causing the slinky to move up and down, but that wave transfers through the slinky to the side. All right, so the molecules are moving up and down, but the movement of the slinky moves it from side to side. That is a transverse wave. The other type is a longitudinal wave. In a longitudinal wave, the wave particles vibrate parallel. That means in line with the motion of the direction of the wave. So in this case, if the molecules are moving side to side, then the wave action is moving side to side as well. This is how sound travels. This is how a spring, imagine this is just kind of a spring, a tightened coil. If you kind of go side to side, the motion of the wave is side to side, and I'm moving my hand side to side as well. I have, if I can find it. Here are examples of each of the two. Okay, so up top here is a transverse wave. In a transverse wave, the particles are going up and down, but the motion of the wave is going side to side. That's perpendicular. In a longitudinal wave, parallel, the motion is in line with the direction of the wave. So if you look down here, this wave is moving side to side, and if you look at any individual particle inside of it, it is also moving side to side. So transverse, perpendicular, longitudinal, parallel. All right, the other type of wave besides mechanical is the ones that are non-mechanical. These are the ones that do not need a medium to travel through, and we're going to spend more time on these in the few weeks from now. We are going to be all electromagnetic waves, light waves. So as light travels through space, there's no air out in space. Light can still travel. It doesn't need a medium to travel through. Same with radio waves. They don't need any molecules to transfer their signal. They can go from one place to another. A microwave, an X-ray, UV rays from the sun, and so forth. Okay, so those will come back in about 3 weeks or so. All right, the parts of a wave. So we are going to start with a transverse wave. These are the ones where the particles move up and down, and then the wave moves side to side. If you're to draw out a transverse wave, there are a couple of important places on a transverse wave. The first one is the crest. The crest is the high point, the highest point on a transverse wave. So a crest is any time you are at your highest peak. All right, so it goes up like this, hits a crest, comes on down, then it goes back up, you hit another crest, and it continues to cycle back and forth. So those are crests. A trough is a low point of a transverse wave. So the trough is where it is at the lowest. So once it goes below to the bottom, that is right there is a trough. All right, a wavelength is the distance from one part of a wave until it repeats. And it is a length. So it's going to be measured in meters. In an equation, we don't write out wavelength, we give it a variable. It is like an upside down Y. It looks like that guy right there. It's the Greek letter lambda. And every time you see it in an equation, it will have this upside down Y that represents wavelength. And then finally, the amplitude is the height of the wave. It helps determine, when we start talking about sound next week, the amplitude of the wave is what determines how loud it is and how many decibels something is. So going back up here to the actual drawing, the amplitude is the height. So you can measure it from here to here, or you can measure from here to here. The distance is the same whether you're going up or down. Most people go from up to the crest. So you measure from this base point here up to the top of the crest. And then a wavelength is from one part of a wave until it repeats. So if I start at a crest, I go down. When I get to the next crest, the distance between, that is known as the wavelength. All right, moving over to the other type of wave, which is longitudinal. In a longitudinal wave, this is going to be a sound wave, this is going to be the spring when you move it side to side. What ends up happening is it has areas where molecules get tightly packed together, and it has areas where they're more spread out. Okay, those two places are called compression and rarefaction. Okay, compression means you have a lot of molecules tightly packed. So in compression, it's the area of greater concentration, in a longitudinal wave. It's each of these places where you have lots of molecules tightly packed together. Okay, rarefaction is the area of lesser concentration in a longitudinal wave. It's where there's molecules are more spread out. So it's going to be kind of these middle places right here. Those are going to be your areas of rarefaction. Okay, these types of waves still have a wavelength. If you pick an area of compression to another area of compression, that's one wavelength. Or if you go from the middle of a rarefaction and another rarefaction, that's one wavelength. All right, so we have a wavelength for both types of waves. You can technically measure the amplitude of a longitudinal wave too, from the amplitude, the height of the wave, but we won't be doing that. All right, so two types of waves. Transverse, the particles go up and down, but the motion of the wave moves left and right, perpendicular. Longitudinal, the particles vibrate side to side, and the wave also moves side to side, parallel, in line with. All right, moving over, frequency. It is abbreviated with an F. You'll see it always gets used italics. So when I type it out, it'll be slanted. It'll be in italics. Frequency, how often something occurs. This is for a wave. It's the number of waves per second. All right, it's how often a wave comes. How many waves are there per second? Waves per second. The unit of the frequency is a hertz. It is abbreviated Hz. All right, so the number of waves per second is measured in a hertz. The higher the frequency, the higher the pitch. So what you're doing when you're singing, if you start at a low note and you go to a high note, what you're doing is you're increasing the frequency with which your vocal cords are vibrating. The higher the frequency, the more times it vibrates per second, the higher the pitch that you're singing. All right, humans can hear approximately from 20 to 20,000 vibrations per second, or hertz. This is our audible range. So as a species, usually we can hear kind of down to 20, and then we can hear all the way up to about 20,000. As you get older, it starts to not be able to get all the way up there. Like I can only hear to about 13,000 before it drops out. Later this week, I'm going to give you a hearing test. So you're going to be able to see, can you hear way down here, and can you hear way up here as well? All right, we're going to come back to this in just a second when we get to the equation. All right, period. If you remember from circular motion, period was the time it took to make a revolution. Okay, period, it's still capital T, and it's still time. Now we're talking about waves. So it's the time it takes one wave to pass, and because it's time, it still has to be measured in seconds. All right, for the equation for period and frequency are the reciprocals of each other. They're the exact opposite. Okay, so if you have 3 waves per second, then every wave takes 1/3 of a second to pass by. All right, so period is equal to 1 over the frequency. Or if you want to, I think this is the one that I have on your equation sheet, but if you want to move your variables around and solve for frequency, it comes there, the T goes under, they swap spots. Frequency is 1 over the period. Okay, so they can just swap with each other. What is the period of a 10 hertz sound? So if you have 10 hertz, 10 waves per second, that means each one comes every 1/10 of a second. So in order to actually mathematically solve it, you just take 1 over the frequency. The frequency was 10. 1/10 is 0.1 seconds. What that actually means is it takes 0.1 seconds for 1 wave to pass. So if you have 10 waves per second, each wave takes 1/10 of a second. All right, and this is the equation that I just used in order to figure out how that works mathematically. Okay, looking at this equation right here, There is another way, another unit that's equivalent to a hertz, and it comes from this equation. So if you look here, frequency, so I'm gonna slide it off. Frequency is measured in hertz, which is the same thing as 1 over time, 1 over a second. Okay, so a hertz is actually the same as 1 divided by a second. It's just another, instead of having 1 over a second, they gave it a new name and called it a hertz. So up here, 1 over a second, box that in, star it, do something with it, make sure that you can find it again when you need it. Okay, so a hertz is the same thing as 1 divided by a second. All right, last thing, we can do some math with waves, but the good news is the math is way easier. Okay, for our wave calculations, you can usually assume waves travel at a constant speed. Okay, think back, a constant speed equation is this v equals delta x over delta t. Okay, but we're now working with waves. We have different variables for distance. The distance of a wave is the wavelength. So as I swap this out for wave variables, over the top, I'm going to put a wavelength symbol instead of delta x. The distance of one wave from before it repeats is the wavelength. On the bottom, the time is the period, capital T. So V is equal to that over that. But we don't really want things on the bottom. So what we can do is, we know that T is the same thing as 1 over an F, the frequency. If we multiply by the reciprocal, we can rework this equation to get the one that we're looking for, which is velocity is equal to frequency times wavelength. That times that, there's your equation. Okay, that's the one that we're going to be using all the time. V is velocity, it has to be in meters per second. F is frequency, that is in hertz, which is the same thing as 1 over a second. And wavelength, that upside down Y, is a length, so it's measured in meters. Looking at this equation, these two are multiplied by each other, which means they will have to have an inverse relationship. And we are going to spend a lot of time on the inverse relationship in lab later this week. But if one of these goes up, the other has to go down. Okay, if you keep the speed the same, increase one, the other one has to decrease. They have an inverse relationship. So if you increase the wavelength of a wave, what happens to the frequency? So V is frequency times wavelength. If you increase the wavelength, the frequency has to do the opposite, so it's going to go down. The next question is what happens to the pitch. Remember from up above, the higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. So if you decrease the frequency, you are also going to decrease the pitch. Okay, and we're going to play around with some musical instruments and stuff, or you're going to watch me or try it at home, and you're going to test this later on this week. All right, last thing. These are the different math equations that you guys are going to be using. Okay, we can use V equals frequency times wavelength. We can use T equals 1 over F. And because waves move at a constant speed, we can also use V equals delta X over delta T. Okay, that's about it for right now. All right, for part A, a piano string tuned to middle C vibrates with a frequency of 264 hertz. It has a wavelength of 1.3 meters. The first question is, what is the speed of the wave? That's V, velocity. All right, so V equals frequency times wavelength. The frequency was 264 times the wavelength of 1.3. And when you multiply the frequency times the wavelength, you should get 343.2 meters per second is a velocity. It's because we have a hertz, which is the same thing as 1 over a second, times a meter, it becomes a meter per second. How long, that's a time, will it take the wave to travel the length of a football field? So delta X is 91.4 meters, and I just found my velocity for this wave to be 343.2 meters per second. The question is, how much time is that going to take? Okay, well, if I wanted to travel a set distance of delta x, then I can use this equation right here, right? It's constant speed for waves, so you always get to use that little equation. You don't have to worry about them accelerating. Okay, the velocity, 343.2 equals 91.4 over t, which is what we're solving for. You have to cross multiply and divide, which means this comes off the bottom, this goes under. You have to take 91.4 divided by 343.2, and when you do, you find the time to be 0.27 seconds. And finally, what is the period of the wave? Period is 1 over the frequency. The frequency was 264. You can leave it in fraction form, but it won't match any of my stuff. I put all my answers in decimals. So then all you do is type it into your calculator, you divide that, and you get 0.0038 seconds because it's a time. All right, that's our new information, the types of waves, the parts of the waves, and the different calculations that we're going to be doing with them. We're going to be playing around with that stuff in lab later this week. Okay, for the problem set, and that is right below it, these questions right here. What other unit is the same as a hertz? You have to make sure you can find that in your notes and know that it's 1 divided by a second, and that is because frequency is the same thing as 1 over a time in seconds. Okay, what is the unit of? This is wavelength. You have to know that that stands for a wavelength, and you have to know it's a length to know that it's measured in meters. If you shake a rope 3 times per second, what is the frequency and what is the period? Okay, 3 times per second. One of the answers is going to be 3, and one of them is going to be 1/3. Okay, frequency is how many waves per second there are. If you shake it 3 times per second, that is your frequency. So the frequency, the waves per second, is 3. The period is the time each takes. It's the reciprocal. It is 1/3. If you have 3 waves per second, each one takes 1/3 of a second to pass. Number 5 is using your V equals frequency times wavelength equation. It's asking you to find out what happens to the wavelength if the frequency goes up. You'll have to go back to your notes. We know it's an inverse relationship, so that should help you solve for that right there. Skipping down to number 6, 7, and 8 are pretty straightforward. We're going to kind of look at some of the trickier ones, and then you'll be able to kind of go back to all of those. So we're going to skip ahead to number 10. All right, number 10, the speed of sound in ocean water is 1,530 meters per second. So V equals 1,530. A sonar signal, that's what measures kind of depth and sees what's underneath the boat, is sent straight down from the ship, and 1.8 seconds later, the signal makes it back up to the boat after bouncing off the bottom. Okay, so here's my artist skills again. Remember, they're terrible. Here's my boat, and then here's the ocean. The signal has to go down, and then it has to come back up in order for it to get back to the boat. Okay, so if it takes 1.8 seconds to go down and up, then each one has to take 0.9 seconds. Okay, we want to know how deep the ocean is. Okay, that's one way. So we can only use 0.9 for our time, not 1.8. All right, so you just have to remember it's hitting the bottom, reflecting back up. You need the time of 0.9. All right, for this, waves move at a constant speed, which means you can use delta x over delta t. Okay, v is the velocity, 1,530. We are solving for the distance. I know this is in the y direction, and this equation is for x. Waves go in all directions. They can go all around, so they don't actually care x or y. So we can plug in and solve for a y or an x in that occasion. And then 0.9 seconds has to go on the bottom because we want just the depth. We don't want it down and up. We want to know just how deep it is. Okay, in order to solve for that, you just multiply the 0.9 to the other side, and you find that the distance that it is 1377, and it would be meters. All right, we are also going to do number 11. So I just want to refresh your memory on the different equations that we can use. V equals frequency times wavelength. T equals 1 over F, and V equals delta X over delta T. For some of these problems, like number 11, you're going to have to use multiple equations. All right, number 11. What is the wavelength of a sound wave that travels 120 meters, so delta X is 120 meters, in a time of, there's my time, 1.37 seconds, and has a frequency, that's F, of 256 hertz. Okay, the question is, what is the wavelength? The only equation that has wavelength in it is velocity equals frequency times wavelength. I'm going to have to use that equation to solve for wavelength. All right, I have the frequency, but I do not have the velocity. So before I can do that, I am going to have to solve for the velocity using my other equation that has V in it, delta X over delta T. I have delta X, I have delta T. I will plug that in to solve for velocity. That will then go right there. Once I know the velocity, I already had the frequency, I can divide over to solve for the wavelength. All right, the rest of them all kind of follow the same path as that, so I will leave you to finish that up. There are a few problems left. That will be your first assignment for this week. The second one will be a lab. We will come back on Thursday or Friday to the Zoom for that or the YouTube video in order to see the different equipment. All right, thank you.